Hello students, let us discuss equilibrium in the chemical processes. Let us consider a reversible reaction, that is A plus B giving rise to C plus D, and the C plus D is giving back to A plus B. It's a reversible reaction. Here the forward reaction is A plus B is giving rise to C plus D, that is called as a forward reaction. And since it is a reversible reaction, that means the products can get back to the reactant. That is called as a backward reaction. In the backward reaction, C plus D is giving back to the reactant A plus B. So in a reversible reaction, there is a forward reaction. That means a reactant converted into the product and which get reversed, that moves in the backward direction by giving the reactant back from the product, as A plus B is again produced from C plus D. So for that reaction, we can say that in the reversible reaction, a chemical reaction reach a state of dynamic equilibrium in which the rate of forward reaction is equal to the rate of reverse reaction, that are equal, and there is no net change in the composition. That means for the reversible reaction, as the two opposite processes, that is the two reaction is taking place in the same rate, that means the rate of forward reaction is equal to the rate of backward reaction. So we can say that there is no net change in the composition of reactant and product, that is A, B, C and D. That is actually we can easily explain through this plot. That means at 0 time we can say that only the reactant A and B are there, that is at the maximum. So when the process begins, we can say that the concentration of reactant decreases. That's why the plot is going down and it becomes parallel after some time. Similarly, when we look at here, as the reactant is, the concentration of reactant is decreasing and it becomes parallel after some time. And when you look at for the cases of a product, that is C and D, initially there was 0 value, but as the time passes, the product concentration of product increases and becomes constant after some time. Because as the reaction begins, the reactant is getting converted into the product. That's why the concentration of product is increasing and the concentration of reactant is decreasing. But after some time, what happens? There will be no change in the concentration of C and D, and there is no change in the concentration of A and B. That is clearly explained in this plot. That is, after this point, we can see that there is a parallel line for C and D. There is a parallel line for A and B. It shows that the value of C and D is constant now. The value of A and B is constant. So the equilibrium stage is attained. We can say that then the equilibrium stage is attained. So we can say that here the equilibrium stage is attained. In this, the rate of forward reaction is equal to the rate of backward reaction. That means how much A and B is converted into C and D, that much of C and D get converted back to A and B. So there will be no net change in the composition. That is in the case of chemical equilibrium. Now let us discuss the laws of chemical equilibrium. Consider a reversible reaction, that is A plus B give rise to C plus D. Here capital A, B are the reactant, capital C and capital D are the product, where small a is the stoichiometric coefficient of capital A, small b is the stoichiometric coefficient of the reactant B, small c are the stoichiometric coefficient of the C product, and D is the stoichiometric coefficient of the product D. So small a, b, c, d, let these are the stoichiometric coefficient of a, b, c and d respectively. So in this we can say that the reaction is actually here an equilibrium stage is attained where both the step is taking place in the same rate. So here which one is the forward reaction? That is a plus b giving rise to c plus d is a forward reaction. So according to the mass action, the rate of that reaction can be determined by the formula, that is rate forward. The forward reaction is equal to Kf, that is a constant. Concentration of A with powers A, that is the reactant A here, its concentration is represented in the square bracket. So if it is written the square bracket, it represents concentration of A. So the concentration of A with powers its stoichiometric coefficient, that is A, small a is its stoichiometric coefficient, that should come in the powers, and the concentration of B and its stoichiometric coefficient in the powers, that is according to the law of mass action here. So the rate is actually is equal to the constant into the product of the concentration of reactant with powers of its stoichiometric coefficient. So that is for the forward reaction. When you write the backward reaction will be like this. C plus D is giving rise to A plus B. This is the backward reaction. So in the backward reaction, what will be the rate now? The rate of backward reaction or the reverse reaction can be written as, that is K R, that is a constant, C to the power C, D to the power D, that is a concentration of C to the power C, concentration of D to the power D. Now we know that in the equilibrium condition, the rate of forward reaction is equal to rate of backward reaction. Here the backward reaction is represented in small r. Rate R is representing the rate of backward reaction. Rate F is representing rate of forward reaction. So when you equate the equation number 2, 1, you get this equation. The Kf, concentration of A to the power A into concentration of B to the power B is equal to Kr, that is a constant, C to the power C, D to the power D. So when we equate this equation, what will be getting here? Because we get the Kc is equal to here is actually Kf by Kr. We'll come up with the new constant here. What is that constant? Kf by Kr is equal to a new constant, that is Kc. So what will be the Kc now when you do the further calculation? We'll be getting Kc is equal to concentration of C to the power C, D to the power D divided by concentration of A to the power A, concentration of B to the power B. So from here Kf divided by Kr, when you do it, you will be getting this equation, that is Kc is equal to concentration of C to the power C, concentration of D to the power D by concentration of A to the power A, concentration of B to the power B. This constant, that is Kc, is called as equilibrium constant, which is represented either Kc or somewhere it is written as Keq, that is the equilibrium constant. So let us discuss this in detail. That is, for the reversible reaction, the equilibrium constant, that is an equilibrium expression, can be written as Kc is equal to C to the power C, D to the power D by A to the power A, B to the power B, where here this is the concentration of C, this is represented as concentration of D, this is represented as concentration of A, and this is represented as concentration of B. So here the square brackets is representing concentration. So here the KEQ is nothing but the equilibrium constant for a given temperature. So the square bracket is actually representing the concentration, that is the molarity. And here the small a, small b, small c and small d are the coefficients from the balanced equation, that is the stoichiometric coefficient. And here Kc, why it is represented as Kc? That is the equilibrium constant in terms of concentration. That is K is a constant, that is in terms of concentration. That's why it is written as Kc. So it states that the law of chemical equilibrium, that at a given temperature the product of the concentration of the product raised to the respective stoichiometric coefficient in the balanced chemical equation divided by the product of the concentration of the reactants raised to their individual stoichiometric coefficients has a constant value. This is known as equilibrium law or the law of chemical equilibrium. So that is nothing but this statement is describing this formula, that is Kc is equal to C to the power C, D to the power D by A to the power A, B to the power B. So this statement is explaining this formula. Let us take one example. Twice NO2 and N2O4, that is in the equilibrium stage at the time. How we write down that is the expression, equilibrium expression for this equation, that is Kc is equal to what is given on the product side, that should be written on the numerator side, its concentration, that is it should be written in the square bracket, and its stoichiometric coefficient should be written on the powers. So what is the stoichiometric coefficient here? That is 1. So the powers will be 1 here, but it is not necessary to mention the number 1 here. But in the case of the reactant side, we have twice NO2. So NO2 should be written in the square bracket, and the stoichiometric coefficient is 2 here. It should be written in the powers. So this is the expression for this equation. So the further examples will be tried, which is given in the textbook. So all of you try such examples for writing the equilibrium expression for the different equation which is given in the textbook. So this is all about this video. Have a nice day.